Right, and I can see everybody has been kicked out. And you're back again. Oh, great. Great that some of you were able to come back so quickly. As I say, I don't know why that happens. Okay, welcome everybody to this lesson. Now, I assume you've all got your booklets that you can start off with. So what we're going to do in this lesson is go through the 3071. Obviously, you'd spend about a week to 2 weeks on it. I'm going to be spending just 1 hour, so it'll be quite quick. I'll be asking you questions, and you can ask in the chat box questions to me, and I'll be looking at the chat box all the time as well, so that I can see what you're asking. So what we're going to look at, just to make sure you're clear what we're going to cover in this lesson, is really we're going to look at what is a redox reaction. Hopefully you'll remember from last year, because this was also done at level 2. And in fact, all of this really we're going to do, except for the very end, is level 2 stuff. We're going to look again at what's an oxidant, a reductant, oxidation, reduction, they sound very similar terms, oxidation numbers, and then we're going to balance some redox reactions. So let's have a look, and hopefully it's going to work. Just before we get on to that chemistry, you'll find with level 3 it's really important to do these 3 aspects of chemistry, especially say when you do a research standard. So whenever you're attempting any task or answering any question, always look at these 3 bits, the macroscopic, so your observations. We'll be looking at a reaction just now, and you need to look at color changes. What was the original color? What did it turn into? Then the microscopic is look at your particles. What is happening at particle level? What are those atoms or species or particles or molecules or ions, those sort of terms? What are they doing? And then under the model, you need to give formulae and equations. So if when you answer, say, an exam question or you do an assessment task, you look at all 3 of those aspects, you're on the right track. If you don't put in very many formulae and equations, and you just go on describing this bit over here, the macroscopic level, then that's not going to help you get a good mark. You've got to look at all 3 bits. Is that clear? Any questions on that? You can just type in yep or no or all good. Okay, I'm just to keep the lesson flowing, I'm just going to really go after the first person's responded, but if you've got a question, type it in, I will be watching. So here is a reaction, so thinking of those observations we were looking at. So it's one I'm sure you've done at level 1 if you were with us. Put some magnesium into some acid, in this case it's hydrochloric acid, and you can see that the magnesium is disappearing. Okay, it's reacting and there are a lot of bubbles. So this is an example of a redox reaction. Let's have a look at what it is. Now, it did say when we first started this video, it said hydrochloric acid, and I just simply put H plus in the formula. If I've got hydrochloric acid, what is the species or the bit that is reactive in hydrochloric acid? The H, the hydrogen ion in particular. Okay, not just hydrogen, the hydrogen ion. So what you've got to be really careful with at level 3 is you've got to make sure that the so I'll just stop that so we don't go into the next one. Okay, you've got to make sure you know how to break up the ions. So just have a very quick check. If I've got HCl, what ions does it consist of in solution? If you can give the charge as well, that would be great. So instead of just saying H, say, so some of you are typing H plus and Cl minus, correct. If I said potassium permanganate, what ions are present in potassium permanganate? So some of you are typing, so I'll just wait for that. Okay, Kira, it's correct that it's a K plus ion, and then permanganate, any ion that ends in H contains oxygen. So I always have a picture of Homer Simpson in my head biting into a donut, an O for oxygen. So he ate a donut. So if a name contains H in it, it contains oxygen. So permanganate will be manganese with oxygen because of the H. Carbonate, carbon with oxygen, carbon H. Okay. You can think of sulfate, sulfur, and oxygen. The trick is knowing how many oxygens to add. That's where the memory work comes in. Okay, so Catherine, you are correct. It is MnO4 minus. Now, why I'm doing this is it's really important at level 3 that you learn those ions. I can send you sheets of pages that you can print out and make flashcards if you aren't sure whether you know your ions, but it is really important that you do learn those, because if you break them up in any other way, you will get a wrong answer. So that's going to be like your homework. If you don't know your ions, start learning. Do one a day, otherwise you're going to get yourself muddled. Email me if you want those flashcards, and I can email you back with that. So I see Kira is typing, but let's get back onto this. So we've done the ions bit. Okay, so we've got, as I say, hydrochloric acid and magnesium. So there we've got the active bit is the hydrogen ions with the magnesium metal. And those bubbles I formed are the hydrogen gas. And then, of course, the magnesium has to react and it forms some magnesium ions. Now, for those of you that remember the redox from last year, why is that a redox reaction? I just want to check how much people know. Okay, nobody's typing, so nobody's too sure. So basically, we've got two parts to this reaction. Those are the two parts. Okay, hydrogen ions is becoming hydrogen gas. So can you see it's gone from a positive to something neutral? Now, if you think of an electron is negative, what do you think the hydrogen ion has done? So I know, Kira, I've seen your that you've responded there to something earlier, but I just want to check. What has the hydrogen ion done to get to H2? It was positive, now it's neutral. It's gained electrons. Okay, so that's really what a redox reaction is. One species, in this case it's the hydrogen ion, gains electrons, and the other species loses electrons. There's got to be a transfer of electrons. So the magnesium was neutral and now is positive. So electrons were taken away. Yep. Okay. Right, so let's basically revise that. So when one reactant, and remember it's the reactants that are reacting, so if there's a transfer of electrons through there, then it's called a redox reaction. Now this is where we need to learn some terms that can be confusing. So the first term I want you to think of is the reductant. Okay, so if that reactant loses electrons, it's the reductant, and the other term is for the other reactant is if it gains electrons, it's called the oxidant. And the way I picture it is with that. So if you think of a reductant, it's one ant to the other ant, the oxidant. And what I've tried to show, reductant starting with the R. Can you see that R in his mouth? Is this ant happy or sad? He's sad. Okay, so if you think of an R, you know, he's got a long mouth, he's sad. He's sad because he has to hand over his electrons. He's losing. Okay, he's losing his electrons. He's got to hand it over to the oxidant. And I didn't give it a full O for oxidant because it made him look surprised. But the oxidant is happy. He's taking those electrons. So I find this image very useful for me to remember what an oxidant and a reductant does. I always just think of an R for a sad face. So a reductant is having to lose electrons. Okay, so let's have a look. I mean to ask you this question, which one was the reductant for the previous reaction? And here's the answer. So I'll ask it to you the other way. Why is the magnesium the reductant? So some of you are typing. Okay, because it has lost electrons, it loses electrons. The magnesium, remember, handed over its electrons to form magnesium 2+, so it lost electrons. The hydrogen is the oxidant because it took those electrons, it gained them from the magnesium, so it is the oxidant, the happy person, the happy ant. Okay, sad ant, happy ant. So that was an example of a redox reaction where it was very easy to see there was a transfer of electrons. You know, the hydrogen ion gained electrons, the magnesium lost. But here's an example where it's not very clear. So while that's playing, so you can see the reaction, you might have done it last year at school, or if you saw the video, if you did it with us last year. So potassium dichromate. Who would like to give the formula for potassium dichromate? Would anybody like to have a try? I'm going to be hammering these ions because you do need to know ions. Good. It's very close, Steffi. It's K. There's something missing. The CR2O part is correct, but 2 of those numbers are wrong. I'm just going to go back. Right, so it's K2, that's correct. So it's K2CrO4, and it's there's no, because it's a neutral compound, there's no charge in it. So it's just K2Cr2O7. It might be easiest if I just put it down like this. Then you can see it straight away. So potassium dichromate is neutral because the potassium cancels out the charge on the dichromate. But if I have the dichromate by itself, it's got a charge of -2, which explains why we need two potassiums. Okay, so there is my redox reaction. Now, just looking at that on the surface, what? Oh, Steffi, I'm saying it's neutral by it. Sorry, thank you for picking that up. The it I'm referring to is potassium dichromate, not just the dichromate by itself, potassium dichromate. So dichromate is negative, potassium is positive, the two together, it's neutral. So just looking at that equation, and I say this is a tricky example, which one is the reductant? Yep, so Steffi, I've just got the dichromate here, not the potassium dichromate, because again, the potassium is what we call the spectator ion, it's not involved. Okay, so you say it's the reductant. Okay, some of you say sulfur and some of you say dichromate. And looking at it on the surface, I can see some of you know your chemistry that you've remembered from last year. Looking at the surface, it looks as though this one has gone from negative to positive. So it looks as though it's lost electrons. Does that seem a sensible, superficial observation? Yep, so remember the one that's lost electrons is a sad face, so it's a reductant. So it looks as though this is the reductant. And this one has gone from neutral to negative, so it looks as though it's gained electrons. So you think, oh, that's the SO2 must be the oxidant. But it actually is not so. That's why I say it's a tricky one. It's not, in the previous example, if I just go back, previous, sorry, I've got to go a few more times, sorry, it's not letting me go all just page by page. Can you see here, I just said elements by itself. So just elements by itself, it's easy to see whether the element has lost or gained electrons. If I go to something where there are compounds, it's not so easy. So what we have to do here, there's my changeover, sorry, my 2 bits. What we have to do here is we need what we call oxidation numbers. Now, who remembers oxidation numbers from last year? Okay, some of you do. Okay, kind of. Okay. Because, as I say, if you just look at the species, it doesn't give you necessarily the right answer. What will always give you the right answer is if you work out the oxidation numbers. So what is an oxidation number? First of all, it's a theoretical number. So it's not a real number. It's looking at the valence electrons of an element and how much it has to share them out or lose them, or how much it can gain them from somewhere else. So it's not an ion truly gaining and losing electrons. It's a sort of a theoretical thing. So let's get an example. Look at carbon dioxide and methane. Now, in carbon dioxide, first of all, carbon. How many valence electrons does carbon have? 4. It's got 4 because it's in group 14, and elements in group 14 have got 4 valence electrons. It's sort of one of the things you know from using the periodic table. You will learn more about that in the 3041 booklet later on, but we'll just leave it at that. So carbon's got 4 electrons, and we know from bonding, in order to become stable, it needs to get a full energy level, so it needs 8 in total. But when I have carbon and it shares its electrons with oxygen to get the other 4 to make a total of 8, oxygen is more electronegative than carbon. Now, do you know what the term electronegative means? Okay, some of you kind of not too sure. Okay, electronegative is the attraction an atom has, or an element has. So it's a property of an element or atom, not of a molecule or an ion. It's of an atom. The attraction that atom or element has on bonding electrons. So carbon is less electronegative than oxygen, which means oxygen has a greater attraction than carbon. You'll learn a lot about this in the booklet 3041. That's the first exam standard. So if oxygen is grabbing those electrons more tightly than carbon, has carbon got less of them? Are those electrons spending less time around carbon, or the same, or more? Less, because oxygen is grabbing them away. So has carbon theoretically lost those electrons? Yes. So of its 4 valence electrons, we're going to ignore the contribution from oxygen. So we're looking at the 4 valence electrons from carbon. Oxygen's grabbed them. So it has lost 4 electrons. So what do you think the oxidation number for carbon would be in carbon dioxide? Well, if it's lost electrons, remember electrons are negative, so it'll be plus 4. Okay, so I can see why the first Catherine said -4, minus being lost, but you've always got to do that double take of electrons are negative, so if you lose negatives, you become positive. Okay, take methane for example now. Carbon has again got 4 valence electrons, and it shares an electron each with each hydrogen. Okay, in this case, carbon is more in any case, carbon in general is always more electronegative than hydrogen. So where are those electrons going to be spending most of their time? The ones that come from hydrogen. Closer to hydrogen or closer to carbon? Closer to carbon. So has carbon gained those electrons from the hydrogen, or is it the same as before, or has it lost any electrons? It's gained. So what do you think the oxidation number for carbon in this molecule will be? -4 because it's gained those extra electrons. So that's what I mean by this. It's a theoretical number. We don't have a +4 charge on the carbon and a -4 charge on this carbon and methane. It's just where those electrons are spending time, is it theoretically lost or theoretically gained? So I hope that idea of what an oxidation number is, you've got that idea. All you have to be able to do is calculate oxidation numbers. You don't really have to know anymore. So let's look at the rules for working out oxidation numbers. And the first rule is, if you've got an element by itself, and it has to be in a neutral form, it can't be in like magnesium ion. If you've got an element by itself, the oxidation number will be 0. So if I've got magnesium metal, for example, the actual metal, it's neutral, I've got that piece of metal, any magnesium atom in that metal has got an oxidation number of 0. What about hydrogen gas? Is hydrogen gas by itself? Is it a neutral? Well, by hydrogen gas, it's only hydrogen and hydrogen. It's not bonded to anything else, and it's neutral. So there's no charge on it. So in that respect, what I mean by like this, so oxygen gas, chlorine gas, they all fit under here. Any metal, iron metal, magnesium metal, copper metal. Sulfur is in the yellow sulfur form, so the sulfur solid. Any element by itself, in other words, not combined with another element, has an oxidation number of 0. Okay, these rules you have to learn off by heart because you must be able to work them out. Oxygen in a compound is -2. Okay, so that's because it tends to always gain 2 electrons. The exceptions are peroxides. Now the only one you work with is hydrogen peroxide, or when it's bonded to fluorine, because fluorine is more electronegative, so it grabs those electrons more strongly than oxygen does. Okay, hydrogen in a compound, so not hydrogen by itself, in a compound will have an oxidation number of +1, and that's because it tends to lose an electron or have it taken away because it's not very electronegative. There is an exception of the metal hydrides, which you don't come across this year. If you carried on with chemistry at university, you will. If you've got a simple ion, like the Cu2+ ion, the Mg2+ ion, or the Cl- ion, the oxidation number is the same as its charge. So if I had the S2- ion, sulfide, what would the oxidation number for sulfur be in sulfide? -2, the same as its charge. Okay, so let's go to the next one. Now sometimes we get given an element that could have different oxidation numbers, so you've got to work it out. The way you do it is, if I have a neutral compound, then like copper sulfate, CuSO4, neutral. I don't know what the oxidation number for sulfur is in copper sulfate. You can work it out by saying that the total sum of all the oxidation numbers of every atom in that species, copper sulfate, must be 0. So that's rule number 5. We will be doing examples in case you're feeling confused and it's rushed. And then if I have a polyatomic ion, so it's charged, it's not neutral, so like sulfate. In the rule 5 we had copper sulfate as an example. Here if we just had sulfate by itself, SO4 2-, there's a charge on it. It's polyatomic because I've got sulfur and oxygen in it, and 5 atoms in that ion. Then the sum of all the oxidation numbers of all the atoms in that ion must equal the charge. So for sulfate, it must equal -2. So I know that's a lot to take in, especially if you can't remember from last year those rules, but they are in the book, so you just have to learn them off by heart, and by practicing a lot will help you remember them. So here are the 4 species we looked at in that tricky example. Let's work out the oxidation numbers for each one. So with dichromate, Rule number 6 said the sum of all the oxidation numbers for every atom is equal to what? So Catherine's typing the charge. Good. And in this case, it's -2. Rule number, I think it was 2, said oxygen in any compound, unless it was a peroxide or with a fluorine, is equal to what? Does anybody remember? -2. Okay, so we can set up a little sum. Great, Jonathan and Brian. There's my little sum we can set up to work out what the oxidation number of chromium is. So it has to equal -2. Each oxygen atom is -2. I've got 7 oxygen atoms, because remember we've got to do the sum of every single atom. And the reason why I've got a 2 in front of the X is because I've got 2 chromiums. Okay, so to work it out, I first say, okay, 2x, 7 times -2 is -14. If I bring it across, it's +14. So -2 plus 14 is equal to 12. If I bring the 2 across, I divide by 2, and I get an answer of 6. Great. Okay. So let's do the next one, which is SO2. SO2 rule number 5. Is this compound neutral or charged? Neutral. So it's rule 5. The sum of the oxidation numbers must be equal to 0. Right. So there's a 0. Oxygen, we've got 2 oxygen atoms. Each one is -2. Would anybody like to work out what the oxidation number for sulfur is? Shown by X. Jonathan, correct. So remember, that's -4 on this side. If we take it across, it's +4. So sulfur is +4. Let's look at chromium. That's a simple one, rule number 4. An iron, a simple iron, you can see it's simple iron. By simple iron, I mean it's not bonded to anything else. It's not a polyatomic iron. That's a polyatomic iron, sulfate. Chromium 3 plus is a simple iron because it's not bonded to anything. So rule number 4 just simply says it's the same as its charge. Well done, Kira. And let's look at this one. We work it out exactly the same as the dichromate. The charge is -2. I've got 4 oxygen atoms in this case, times -2. So if you work it out, -8 going across is +8, and it becomes +6. Good, Jonathan. Can you see the point I was making earlier about knowing your ions? You do need to know your ions. Okay. Right, we will be working out some oxidation numbers a little bit later, but do you have any questions on this before I move on? Nope. Okay. Right, I'm just checking the time so that we don't go over. One of the questions students often don't know is working out possible products. Like, would a possible product be, I mean, I gave you the products that it was a sulfate and it was the chromium 3 ion, 3 plus ion, but you may not know that. So how could you work it out? Your periodic table can help you a lot. And if you look at the number of valence electrons that there are. So hydrogen has got how many valence electrons? A hydrogen atom. 1. Okay, so hydrogen can either gain 1 electron to form the hydride, which is not that common because hydrogen doesn't have a very strong attraction to electrons, but it can either gain an electron to get a full energy level, or it can lose 1 electron to form the hydrogen ion. So could I ever get an oxidation number of hydrogen of +5 or +4 or anything like that? No, because it just doesn't have enough electrons to lose. And can I ever get an oxidation number of -3 or -2 for hydrogen? No, because it can't gain more than 1, because once it's gained 1 electron, it's got its 2, you know, it's 2 2 electrons it can have to make that first energy level full. So if you're trying to work, if you've got hydrogen as your substance, say the hydrogen ion, the only thing it can form is hydrogen gas as an H2, or perhaps a hydride. But as I say, as far as you're concerned, you don't have to know about hydrides. And if you had hydrogen gas, the only thing it can really form is the hydrogen ion. Similarly for oxygen, oxygen is in group 16 of the periodic table, and in its neutral form of oxygen gas, it's got an oxidation number of 0. Now the peroxide is the case when it gains 1 electron. That's why peroxides aren't very stable, because oxygen has had to fiddle the books to try and get a full energy level. It's sort of only gained 1. But that is an option it can form, or it can gain a maximum of 2 electrons. So you'll never have oxygen with an oxidation number of -3 or -4, because it can't gain anymore. And as I say, you'll never really get oxygen with an oxidation number of +1 or +2 or higher, because it tends not to lose electrons. The only element it'll lose electrons to is fluorine. So if you had oxygen difluoride, then oxygen has a positive oxidation number. But again, you won't be involved with that, have to deal with that. So as far as you're concerned, that's all what you have for oxygen. That's rule number, I think this was rule number 2, and that was rule number 3. Okay, now here's a periodic table for all the other ones. Use it to help you work out if your answer would be sensible. So let's take chlorine, for instance. Can chlorine ever have an oxidation number of -2? No, because chlorine can only get 1 more electron, so -1, to get a full energy level. So if I had a chloride ion, so the chloride ion, its oxidation number is already -1, okay, can chloride gain... Oh, is anybody else having a problem with the slideshow? Kira, you may... I'll just check if you're in or out the class. Ah, you've dropped... No, you're back in. Okay. Right. Sometimes you drop out and you've got to come back in again. Yeah. Okay, so with chloride, would chloride gain any more electrons? No. So chloride can never gain more electrons. It can never be an oxidant. So it can never have a smiley face and grab more electrons because it's full. Okay. Can chloride be a reductant? Can it lose electrons? Yes. And it can theoretically lose up to 7 electrons. Okay, so it's a theoretical number. You'll never get a Cl plus 7 ion, but theoretically you can form that in a molecule where chlorine doesn't get a big share of its electrons. Fluorine, being the most electronegative, is either 0 or -1 for fluoride. It never is anything else. So that's the one that has the only 2 oxidation numbers, nothing else. Oxygen we've already dealt with. Any of these others can have a variety of oxidation numbers. So nitrogen can gain electrons until it's full, or it could lose electrons. So it could have an oxidation number of +1, +2, +3, or +4. Sorry, would also be plus, and then of course, because that means it's got 1 electron left, it's got to go 1 out to get an empty energy level +5. So nitrogen can never be more positive than +5, because it can only lose up to 5 electrons. Over here is when it's empty. Okay, so as an example, there's sulfur. So taking sulfur, it's in group 16, so it can have oxidation number up to -2, or, and just the way it works, it goes in even numbers, it goes +2, +4, plus 6. Okay, if you've got any species like we saw with sulfate, would sulfate ever lose more electrons? Would it ever be a reductant? Remember the sad face for reductant, losing electrons. Could sulfate ever be a reductant? Okay, now I see Catherine and Jonathan have said yes, but I think that was to a previous question. Okay, yeah, so Kira, no, it can't. Because it can't, it's lost all its valence electrons. It's already on plus 6. It can't lose anything more. So hopefully that sort of gives you an overview of what's possible and what's not possible. Use a periodic table just to help you work out whether something is an oxidant or reductant. Now, so just going back to working out if a substance has lost or gained electrons, okay, once you've worked out the oxidation numbers, you can work out if that species has lost. Remember, we went from SO4 to SO2 and it looked as though it had gained electrons because it was going from neutral to negative. Now, once we know the oxidation numbers, we can see the oxidation number for sulfur is plus 4, but the one for oxidation number for sulfur and sulfate is plus 6. So have we become more positive or less positive? More positive. And remembering that electrons are negative, have we lost or gained electrons by going more positive? We've lost. Okay, so the more positive you go, the more electrons you've lost. Okay, so SO2 here, if it's lost electrons to form sulfate, is SO2 a reductant or an oxidant? So think of sad ant, happy ant. So some of you are typing, that's what I'm just waiting for. It's a reductant, correct. And the other way is, you've always got to have one reductant and one oxidant. You can't both lose because it has to be a transfer. So with dichromate, the chromium, remember, we worked out was plus 6, and it's become plus 3 for the Cr3 plus ion. So dichromate has gained electrons. It's become more negative. Less positive, more negative, same thing. Okay, so it's gone from plus 6 to plus 3, so it must have gained electrons, which means it must be the happy ant. It's gained electrons, so it's an oxidant. Okay, any questions before we move on? Nope. Okay, so now I'm going to ask you questions. So very quickly, just have a guess at the first one. Has the Br2, because when I say whether a substance has lost or gained electrons, remember we're always talking about the reactant. The product is only important to work out whether electrons have been lost or gained. But has the bromine lost electrons, the permanganate lost electrons, and so on. So you're going to have to work out some oxidation numbers. But the first one is fairly simple. So has the bromine lost or gained electrons? Can you see it's gained? It's simple because it's gone from neutral to -1. Bromine is by itself, so its oxidation number is 0. Here it's -1, rule number 4. It's gone from 0 to -1, gained. Okay, so it's gained there. Permanganate. Does anybody want to work out the oxidation number of manganese and permanganate? Okay, it's +7, correct. So if you're not sure how to work that one out, try and work it out. I don't want to slow the lesson down too long. You can always review the lesson and look at it. So it's gone from +7 to +2. Has it lost or gained electrons? Okay, it's gone from +7 to +2. It's gained, because if you think of a number line, it's becoming more negative or it's becoming less positive. Does that make sense? Okay, so it's actually gained as well. Don't let that negative sign there put you off. Think of this as +7 going to +2. Here's one. Remember, this is now, you've got to recognize it as a peroxide. So what is oxygen in a peroxide? When I say what is, I mean what is the oxidation number of, okay, it's -1 and it's going to -2. Steph, I think you're getting a bit ahead, so it's going from -1 to -2, so it's become more negative, and so I think I did something wrong there. It's gone from it's gone from, at least when I did this PowerPoint, my brain was working. There it's -1. What is the oxidation number of oxygen by itself? Is it -2 or is it 0? Yes, thank you, Catherine, that's 0. It's rule number 1. So rule number 1, where it's, if an element is by itself, it's 0. Steffi, I had exactly the same thing. I was thinking of -2. So it's gone from -1 to 0. So it's become more positive. So it's lost electrons. What about iodate? Okay, iodine with oxygen is iodate. Remember, anything with 8 has oxygen. I've just suddenly seen number 6 is exactly the same as number 2. Okay, iodate to iodine, iodide. Can anybody work out the oxidation number of iodine in iodate? 5. That's correct. I hope everybody else agrees. Otherwise, you can look up the oxidation rules and look it up yourself, because it's 3 times -2 is -6. It's all got to equal to -1, which means I is 5. So if it's going from +5 to -1, has it lost or gained electrons? Gained. Okay, right. And here's iodide going to iodine. So it's in a way the reverse of what we had at the top, and it has lost. And sorry, I never realized, I meant to obviously redo that one. So we'll ignore that one. It's obviously lost again. Now, we could work out what are the reductants and what are the oxidants. So if bromine has gained electrons, is it a reductant or an oxidant? Is it a happy ant or a sad ant? It's an oxidant, okay? Smiley face, happy ant, okay? And so any of the gained will be oxidants, and any of the lost are the reductants. Now you'll notice the species is the oxidant. So here the element is the same as the species, bromine. Here a common error is people will say manganese is the oxidant. Is it manganese or is it permanganate? That's the oxidant. It's permanganate. So when we talk about oxidant and reductant, it's always the reactant, and the reactant in this case is permanganate. The element manganese has changed its oxidation number, but it's only in that form of permanganate. So you've got to be specific that permanganate is the oxidant, and don't just say manganese. Or iodate is the oxidant, not iodine. Right, so put that in the back of your mind of reductant and oxidant, because now I want to look at 2 other terms, reduction and oxidation, and they're different. Okay, so I think the easiest is just to learn this by mnemonic first of all. Oxidation is loss of electrons, reduction is gain of electrons. So the mnemonic you use is oil rig. Have people come across this oil rig mnemonic before? Yep. So oxidation is loss of electrons, oil. Reduction is gain of electrons. So think of an oil rig. But if you have a look at those 2 things that we looked at, reductant, and now we're looking at reduction, can you see the difference? And this is why students, I think, find it so confusing, because they seem to contradict each other. Reductants lose electrons, But a reduction, which is the process, reductant is the species, the reactant. Reduction is the overall process. In a reduction, there's a gain of electrons. So just to add some more words into the mix, an oxidant, that's that one over there, he gets the electrons. So he's being reduced. Doesn't mean he's getting smaller. Okay, he's just being, it's just a chemistry term that they use. An oxidant is being reduced because it has gained electrons. So an oxidant is always in the reduction part of the reaction. Okay, similarly a reductant, so this is this sad reactant ant, he's losing electrons. So because he's losing electrons, he's being oxidized, oil rig, and so a reductant is always in the oxidation part of the reaction. Is that clear? Do you think those images and those mnemonics will help clear it up? Or are people very confused? Quite a few times, a little. Okay. So I find it's easiest if you remember reductant and oxidant first, and then you just think of sad and happy ant, and those are the reacting species, and then think of the oil rig. Steph, I'll most probably put it up tomorrow. Mondays and Tuesdays I'm not in at work, so if for any reason I can't do it up by Friday at the latest, it'll have to go up on Wednesday, but I'll really try to make it on Friday, and I'll try and put it on YouTube as well, so because I know for some people they find it easier. Okay, so let's go over this again, because reduction, reduce, reductant, it looks, you know, and we know, and of course reduce, you always think of meaning smaller, and chemistry doesn't mean that at all, so it's, I can quite see the trickiness. So if we go to that original easy example, the hydrogen is the species, the hydrogen ion. It has gained electrons to become neutral. So this species here is the oxidant, okay? But that part of the reaction where the hydrogen ion goes to the hydrogen gas is the reduction half reaction. I've tried using color coding so it's sort of easier to see. So the oxidant is always sitting in the reduction half reaction, and the reductant, which is a magnesium, you know, sad face, losing electrons, he's always sitting, or it's always sitting in the oxidation half reaction. Now, remember we said redox is a transfer of electrons, so we need to show those electrons being transferred. You can see also our equations aren't balanced. We've got the right number of atoms, but our charges aren't balanced. We've got 2 positives here and a neutral there. Oh, sorry, I forgot. There was one more thing I meant to add in. It's there. It didn't come the right way. So there are the 2 electrons that I need to, that it's gained to form the hydrogen gas. The magnesium has lost those 2 electrons. So can you see for the oxidation, the electrons are always on the right-hand side, and for reduction, they're always on the left-hand side of the equation. And what that previous thing said was, if I just go back, hydrogen ions are reduced to form hydrogen gas. That's just the terminology we use. And magnesium metal is oxidized to form magnesium ions. So, and then as I say, oxidation, reduction, it's always a half reaction. So you'll always have electrons showing in it, and it only shows half of the total reaction. And do you notice it contains the reactant and the product? So it's got to have both. It's got to be a reaction, reactant going to product. If I do the other one, there's my oxidant and my reductant. My sulfur is losing the electrons. The chromium in the dichromate is gaining those electrons. So I can do the same thing. My oxidant is in my reduction. My reductant is in my oxidation. And then you'll notice the oxidant and reductant are always a reactant. They're always on the left-hand side. And it's a species. So it's not necessarily an element by itself. It's always a like dichromate or SO2 or hydrogen ions. Any questions before we carry on? No. Okay. Right. So in the last 10 minutes or so, we'll balance the redox reactions. So if you remember from last year, it might be easy, or otherwise this will be the first time. I will tell you that the task for this level 3 is not hard, so don't get too stressed if you're getting confused. So if we take that first one, that's an easy example. You could all balance that one by inspection, I'm sure. How would you balance that? Just by looking at it, what would you do to make a balanced reaction? By balanced, we mean the same number of atoms on both sides and the same number of charges on both sides. Put a 2 in front of the H+. Correct. So there you go. That's balanced. Then let's carry on. But I want to use this example to show you the steps for the redox, because when you get to a tricky one, like we had with the dichromate, you can't just look at it and give the answer. So what do? We first look at the half reactions. So what are my half reactions? It's, the first step for each one is the atoms. So in the reduction, I've got H plus going to H2, and I've got to put a 2 in front. Okay. For my oxidation, I've got an Mg going to Mg2 plus. I've got one magnesium. Those atoms are balanced. So my atoms are all balanced now. Now I must balance the electrons. So with my electrons, that's when we put in the electrons, because a half reaction always has to have electrons in it. So there it is. I've got 2 positives. So in order to make my 2 positives neutral, I've got to add in 2 negatives. And similarly over here, in order to balance out this charge, because I've got a 0 over here, I've got a +2, so I need a -2. Each electron is negative, so I've got to add 2 electrons, and that will balance my charge, and I can do a final charge balance. And can you see hydrogen over here is neutral, so it's got a charge of 0, and 2 positives plus 2 negatives gives you a total charge of 0 on the left hand side. Similarly over here, magnesium metal is neutral, so it's 0. Whereas here I've got on the right hand side 2 positives plus 2 negatives makes it a total charge of 0 as well. So first half reactions, then you add them together. So here's my balanced reduction half reaction, my balanced oxidation half reaction. Now we have to add them together. Now just like any equation, if I add them together, you just bring them down. So I'll bring in the 2 plus down, Mg down. But can you see I've got 2 electrons here, and I've got 2 electrons on the other side of the equation. It's a bit like saying A plus B is equal to A plus C. How could you simplify that equation? You cancel them. You cancel the thing that comes up the same side, so it's like the A's, or in this case it's the electrons. So those cancel out. 2 electrons will cancel out 2 electrons. And now, as I say, you just bring them down, 2 plus, 2H plus, an Mg, an H2, and Mg2 plus. And that's more or less done. But remember, always check. So atom check. You always do atoms, electrons, charge each time. I've got 2 hydrogens left hand side, 2 hydrogens right hand side, 1 magnesium left, 1 magnesium right. Electrons, I've got no electrons left in my full equation. All my electrons must have cancelled. If they don't cancel, I've done something wrong. And then charge, my charge on the left must equal the charge on my right. So in this case, 2 positives plus a neutral makes 2 positives. A neutral plus 2 positives makes 2 positives. So each side has got +2. Okay, let's finish off with the other one. This is the dichromate, and it's the same thing. Oh, before we carry on, it didn't say in that original equation that we were using acidified dichromate. It is actually acidified, and if you think of what is an acid, if we acidify something, what are we adding? I've given the answer there really, right in front of me, H+. Because as remember, an acid is a proton donor or it's a H+ ion. So we can, when we balance equations, we can add H+, and this is also happening in solution. You saw it was in solution. And so what other substance is present in my solution? It's a very obvious one. In other words, the solvent. So if I've got a, well, no, I don't. With oxygen, you've got to be careful, Catherine, because by oxygen you mean oxygen gas. So that you've just got to think of what species are present rather than what elements are present. So if you think of, if I've got an aqueous solution, what is my solvent? Well, we don't necessarily have oxides present because we haven't added an oxide. So if I use the term aqueous, what does that mean to you? So I just have to have water. Water. Okay, H2O. Obviously my subconscious was working on me there. So I've got lots of water present because the whole thing's happening in water. So water can also take part in the reaction. So if I've acidified it, H+ can be a reactant, and of course the water will always be there, so it can be a reactant. Anything else like oxygen or oxide, I can't use because I haven't added those particular species. I haven't added oxygen gas, I haven't added oxide, so I can't use them. So let's start balancing first. Now we'll just do the dichromate one. First of all, we've got 2 chromiums here, so we've got to add 2 chromiums in there. Now, to balance the oxygens, because we didn't have oxygen present on the left-hand side, you can add them in the form of water. So 7O, I can say 7H2O, that gives me 7 oxygens. But is it totally balanced now? What element is not balanced? The hydrogens. So remember what I said, we can use H+ as a reactant. So I just simply add 14 hydrogen ions to make this reaction work. Then the next step is to balance electrons. How many electrons do you think I'm going to need to add to make it the charge is equal? So here I've got neutral plus 2 times 3, so I've got plus 6 on this side. So how many electrons do I need to add to make this total charge equal to plus 6? Kira, just think of the 14 electrons. I agree the 14 E's would cancel that, but we have got -2 there as well. So we've got -2, so we've got 2 negatives, 14 positives. So overall, how many positives have I got? I mean, or what's my overall charge? So I've got 12, so I've got to add 12 electrons. Blah, blah, blah. I said the. Have I made a mistake here? That should be 12. Sorry, I made a mistake. Ignore that. Does it 14? Yep, that should be 12. Does that make sense to you? Sorry, no, I did get it right. I can see my brain is not working. Sorry, I'm doing chemotherapy at the moment, and my brain sometimes just stops working. So, right, that is correct. This charge has to equal that, and that, of course, is plus 6. So you've got to say 2 negatives, 14 positives must be equal to plus 6. So, Catherine, well done for being onto it. Jonathan, well done for being onto it. So I'll just say it again in case I've confused the others. I've got 2 negatives there, I've got 14 positives there, but my overall charge must equal on this side, so it's plus 6. And if you do the sum, I need 6 negatives to, oh, that went wrong there, let me go back. I need 6 negatives there to make this total charge a plus 6, because that side's plus 6. Okay, so let's do it again on this side, and then hopefully that'll clear things up. So again, first atoms, sulfur has been balanced, so that's fine, but oxygens have not. So remember, how do I add more oxygens to the left-hand side? Because I'm too short here. In what form can I add oxygen? I can't add it as oxygen gas, and I can't add it as oxide. I can only add it as water. Great. So I need to add 2 waters to make my oxygen equal. And how do I balance my hydrogens? So 4 hydrogens to the right. Yep, because I've got 4 hydrogens on the left-hand side, so 4 to the right. Now I've got to do my electrons, because my atoms are now balanced. I've got to make the charge on this side equal to the charge on that side. So if this is 0, neutral plus neutral, 0, I've got to make this total charge 0. So what do I need to add to make this right? I add 2 electrons to the right, because 2 negatives plus another 2 negatives, or 4 negatives plus 4 positives is 0. So in this case, both sides are equal to 0. The previous time they had to both be equal to plus 6. Now it's 0. And we now have to, so we're going very slightly over, I'm sorry about that. So very quickly, we've got to add them all up. Now, what do you notice about my electrons? Will they cancel? No. So I need to increase the number of electrons in this oxidation half reaction. So Catherine, correct, I need to multiply by 3. So there it's all the way. So 3 times 1 is 3, 3 times 2 is 6, 3 times 1 is 3, 3 times 4 is 12, 3 times 2 is 6. And can you see the electrons will now cancel? 6 electrons will cancel 6 electrons. However, do you also notice I've got 14 hydrogens and 12 hydrogens? Now, we don't want to be sloppy and have tons of the same thing on both sides. We want to cancel things out. Similarly, we've got 6 waters and 7 waters. So can you see all 12 hydrogens will cancel out with 12 over there, leaving me with 2 left. So I've got no hydrogens down here anymore, but I've got 2 hydrogens there. And can you see with the water, all the water down here is going to cancel with 6 of them up here, leaving me with 1 water left. And if I add it up, dichromate, 2 hydrogen ions, 3 sulfate, 3 SO2 molecules, that's all been cancelled. 2 dichromates, 1 water, and 3 sulfates. And that is a balanced equation. Now in the booklets there's lots of practice for you to balance. So as I say, we've done 1 to 2 weeks work, 1.5 weeks work sort of in 1 hour. So if you're a little bit lost, you've done really well for just being a little bit lost. Any questions? Because we have actually gone slightly over. Okay, while Michael is typing, next week we'll be doing the last 2 lessons of 3071, which is comparing the reduction potential values, and the beginning of 3072. Can you see what standards you're doing? Right, Michael, this is the 913. So I'll be fancy over here. Hopefully this will work. So hopefully you can see this. The standard is the 9. Whoops, daisy. Just got this thing and I'm trying to work out how to use it. 91393. It's the internal. So sorry. I've got to learn how to do this. Sorry, I got this just this morning. And that looks terrible. I'll be hopefully better next time. I'll leave that. So it's the internal standard. It's worth 3 credits. And I think I shall just get rid of that little thing. Okay, so hopefully by the end of this first term you'll have your 3 credits and you would have started the external already, the first external. Any other questions? Okay, I'll send out, or I'll put up on Ottle the link for the recording, and otherwise next week I'll be sending out the reminder on Wednesday with the link as well, the recording there. Kira, what external is first? The 3.4, which is the 91390. It's the one on properties of molecules and shapes of molecules and so on, and thermochemistry. It's worth 5, all the externals are worth 5 credits at level 3. Right. Okay, and as I say, you're welcome to email questions for us to do at a lesson, or to ask at the beginning of the lesson, and we can deal with that before we carry on. Otherwise, we've gone now rather a bit way over. Have a very good rest of the week and a weekend. Bye.